All right, it's 9 a.m. So let's get started. Welcome to PLDI Thursday. I hope you had an awesome, PLDI Wednesday, first day of PLDI, and got to check out some of Boulder last night, I hope. So I wanted to flash again the Sick Plan Cares slide again, because I wanted to just emphasize how important it is to us to build an inclusive and welcoming community at PLDI. So again, the people in yellow are the folks who are part of the Sick Plan Cares Committee, including our chairs, Sukyeon and Steve, who are here. Again, if there's anything you want to talk to about the Sick Plan Cares community, these are the folks, and they're all wearing these red signs. Okay, so in terms of events today, there's the LGBTQ lunch in Ajax Tavern, which is the hotel restaurant, which is just across on the other side of the lobby at the end. And then we have an exciting industry session here in this part of the room, and Flatirons 2 at 3:50. And then this evening is really the PLDI business meeting at 6 p.m. And then immediately following the business meeting is the awards dinner, which will be over here in the lunchroom, plus spreading out into the lawn and so forth. Okay? All right. So the LGBTQ lunch will be led by our inclusion chairs, Willow and Christine. All right. Also, to continue this year's PLDI meetups, where it's an opportunity to welcome newcomers and mix with the old timers. Right. Dakota, or one of our social chairs, will be leading a walk after the industry session before the business meeting to see the Dusanbe Tea House, if you haven't gotten a chance to see that. It'll probably be, with a large group, you probably can't get seating inside, so it'll probably be on the patio, but you can go in and order a tea from the bar or something like that. Okay? As usual, meet in the Flatirons foyer and follow the group. All right? All right. With that, I don't want to take any more time, and I will hand it off to Manu to introduce our second keynote speaker.
Okay. Hi, everyone. Good morning. It's my absolute pleasure to be able to introduce our second keynote speaker, Professor Myung Kim. Myung is a professor of computer science and the vice chair of graduate studies at UCLA. And Myung has a long track record of really interesting and impactful research. So she did some very influential early research on detection and remediation of code clones in software. And so when I think about copy-pasted code, my immediate instinct is, oh, this is terrible. We need to just get rid of this. But Myung saw an opportunity to build really cool new tools that do bug finding and refactoring, API migrations that kind of handle these clones as they exist. And I think you can draw a very direct line of influence from Myung's work on code clone detection to work on the naturalness of software directly to all the AI coding agent tools that we have today. And recently, Myung's work was recognized with the IEEE TCSC New Directions Award. She's also led early and influential research on the role of data scientists on software teams. And her current research focuses on developer tools for data and compute-intensive systems. So Myung's an ACM Distinguished Member, and I also wanted to mention that she's been recognized with the ACM SIGSOFT Influential Educator Award for her strong mentorship record. Her former students are incredibly successful professors at all kinds of top institutions. One of my great colleagues is one of her former postdocs. So we're thrilled to have her here. Welcome, Myung.
Thank you, Anu, for generous introduction. It's really my pleasure to be here. When I was invited to give this keynote, I initially thought about combining my last two keynotes from automated software engineering and International Symposium on Testing and Analysis on software engineering for AI, and then updating with my group's paper in the last 3 years. It would have been a safe choice. But AI is changing world so fast, and there is a story of a critical bottleneck that I wanted to talk about today. So in preparation for this keynote, I prepared some new materials and new research results to support some of the hypotheses for this keynote. So in the beginning of this year, I read this book called The Happiness U-Curve by Jonathan Rauch. This book is about scientific observation that human life satisfaction has a U-shaped trajectory. In our youth, like we are biologically wired for like high expectations and ambition. And in the 30s and 40s, we realize that achieving the dream that we once had doesn't make us as happy as we thought, creating this gap of a disappointment. In the United States, this rock bottom of a happiness U-curve is age 47. I just celebrated my 47th year birthday 2 weeks ago, so I'm at this absolute nadir of happiness U-curve. So when I started my graduate school in early 2000, I had an opportunity to study copy and paste programming practices and evolution of code clones and recurring code patterns. And looking at the rise of open source repositories like on the internet, I had a dream. Like, maybe one day it would be a wonderful world if we could automate bug fixes, generate code, perform large-scale migration and refactoring, all by leveraging code regularity. I thought that would be a wonderful world. Fast forward to 25 years later, we live in such world. A lot of these large-scale migration, bug fixes are all happening by leveraging the power of AI or massive regularities that are seen in the code repository. But despite receiving this award on opening the new direction of a data-driven software analytics and code clones, and also, my proud academic baseball card of producing 8 professors, like 5 of them being NSF Career Award winners, I could not deny irrelevance of what I have done, what my students did, and also what my friends did in our community. Looking at this like LLM, I couldn't find any trace of abstract syntax tree matching, program dependency graph analysis, or any kind of a program analysis like really built into this logic. Rubbing salt on this open wounds was increasing fear that the days of academic software engineering research might be ending soon. It seemed that the brilliant research these days is done by the industrial power of a massive data set, endless GPUs, and these days, just abundant tokens. However, despite this fear, the very power of AI was transforming the lives of people around me. This is just a first-hand observation and anecdotes from people around me in the last 2 months. One of my professor friends tried to vibe code the world's best model counting solver in Rust in a programming language that he didn't write a single line of code before. My own husband, driving from LA to San Diego, he is a startup entrepreneur, vibe coded Monte Carlo simulation on qubit data while he's driving. Then I saw applied scientists in our team at AWS like prototyping symbolic execution engine in 3-week sprint. As a person, or those of you who try to extend or modify symbolic execution engine like me, we know how hard and difficult it is. And this is just like the statistics I found, from some of the repository that I saw in the recent month. Some of these commits are like 10,000 lines of code per commit, almost 100 lines being modified. Incredible velocity. There's only 20 working days in a month, but there is 30 commits happening within a month. And a lot of these files are actually agentically generated. So there's YAML, JSON, Markdown MD, but also like lots of code as well. So are we all happy with this vibe coding? or this power of an AI revolution. When I went to ICSE, International Conference on Software Engineering in Brazil this year, some of my friends and colleagues are concerned. In fact, the study from Anthropic found that, when you did the studies of people who rely on AI, after coding, if they do the skills test on the very concept that they coded, there's a 17% less on a quiz score for the group that relied on AI. The study from Georgia Tech found that there is an increased attack surfaces not only created by this large code footprint, but the AI coding model is used as actually vehicle for propagating vulnerability and security vulnerability. And really interesting study that came out this year from researchers at CMU, they studied the cursor-enabled project on open source repository, almost 800 repository on the GitHub. And then they found that Vibe coding adopted projects had an incredible velocity in the first 2 months. 3 to 5x increase in coding velocity, but it tapers off soon after 2 months. And then they are left with a 30% increase in static analysis warnings and 40% increase in code complexity. And my colleague, Professor Peggy Story, now warns us the cognitive debt, not just the technical debt, which means that what really made software wonderful was this team that was behind the software with the shared understanding of the code. But as we are moving into this new space, there is erosion in shared team's understanding. So in my opinion, validation is a new bottleneck in AI. Every tool that makes a creation cheaper and inexpensive makes validation more expensive. And I'm not the only one who's talking about this. There's a blog like, the TED Talk or, a podcast that warns how AI raises the cost of verification. And the recent keynote from ICSE, by Qinghua Lu, says the bottleneck in AI engineering is no longer producing behavior, but verifying the behavior. So this is a diagram I drew to just talk about this transition. Previously, we were coding at the human pace of writing code. As we write the code, we think about it, we reason about it. There's a lot of emphasis or effort that go into part of the coding process. And as we are moving towards this new space of agentic AI software engineering, I think the coding itself is actually done by speed of agent and AI. And that bottleneck is now shifting to the specification or intent, the definition, and validation that checks whether that intent works on the software that is being built. All right, so this is the rest of my keynote, what I'm going to talk about today. I'm going to first describe my experience of fuzz testing and property-based testing at UCLA and Amazon Web Services. And based on the experience, I'm going to argue that we must solve the specification problem. Then, I'm going to describe my hypothesis about recurring property patterns or recurring validation pattern to amplify or solve this specification problem, and then share some of this preliminary results that I generated for this keynote to support this hypothesis. All right. So now I'm going to, based on my experience of this fuzz testing and property-based testing at AWS and UCLA in the last 5 years, I'm going to argue that well-formed input generation is absolutely necessary, but it's only half of the game. And to increase actionability, we must solve the strong oracle problem. All right, so before we get into the talk, let's be on the same page by talking about the terminology. So fuzzing goes back to 1988 by Barton Miller, who's a systems researcher working on Unixes. He created this notion of a fuzzing where you blast a program with the randomly generated malformed input to see whether it will lead to crash or leak memory. And these are using these shallow or weak oracles, such as crashes and hangs and runtime exceptions, or memory safety errors as a signal of failure. Property-based testing, on the other hand, like, based on the seminal paper in early 2000 and quick check, talks about the idea of a randomly generating input, but in a well-formed input. And there is a corresponding strong oracle that says, given that well-formed input, what the behavior system should be on the execution. So, about like 12 years ago, I had the opportunity to study emerging role of a data scientist in software teams at Microsoft Research. And as I was recognizing that we need to really focus on data-intensive software development, I worked on set of a new research agenda on debugging and testing for data-intensive computing systems such as Apache Spark. And if you look at some of the last 5 years of my work, I would say that there's a lot of words, fuzz testing that's appearing as a publication. And I realized that some of these data-intensive development is really powered by incorporating hardware heterogeneity, such as like GPU, FPGA, or ASIC. And so I kind of shifted a little bit towards this direction as well. And if you look at the last few years of work, again, you are looking at the words with the fuzz testing on let's say MLIR compilers, hardware compilers, or incorporating hardware heterogeneity. So what is these domain-specific fuzzers? At a 10,000-foot view, specializing a fuzzer involves usually making adaptation in one or more of 3 dimensions. So imagine AFL, or American Fuzzy Love, which is a kind of standard mutational fuzzer with the feedback. What specialized fuzzer will do is either generating and mutating input in a valid form or high chance of generating valid input. You generate new coverage or feedback guidance signal beyond branch coverage to guide the search space in a very careful manner, but at the same time, reduce overhead and runtime latency involved with the repetitive invocation, which is really important because the fuzzing is iteratively very iterative. So you may be wondering, then why build a domain-specialized fuzzer? It's because the fuzzers cannot really distinguish ill-formed input from incorrect output. Because the fuzzers rely on shallow or weak oracles, such as crashes, hangs, runtime exceptions, and memory safety errors. So let's look at this example coming from one of our recent papers. If you try to fuzz MLIR compilers or hardware AI compilers built on MLIR framework, if you use a base grammar, you generate string like that on the top. The likelihood of generating input that fits a specific dialect, such as a hardware dialect with its own grammar, own semantics, the chances are almost near 0. So in the last 3 years, in software engineering community, this semantic fuzzing or semantic input generator became popular. What these tools do is it provides languages and tool support to produce well-formed, constraint-satisfying input. There are techniques like a Fandango or ISLA coming from Andrea Zeller's group in CISPA. My group worked on some of this technology, like a programmer or SenseFuzz. And you could also think of a well-formed input generator coming from inductive relations, like in proof-assisted languages, such as a QuickCheck or a Specimen, in one of those categories of a tool. On the right, you are seeing the example of a Fandango DSL, where it allows you to specify context-free grammar, but allows you also specify semantic constraints, such as a diffuse constraint, using specific languages that could guide the input generation during the evolutionary fuzzing. So at Amazon Web Services, our team worked on one of this well-formed semantic input generator. And there was a target use case context. At AWS, the API authorization is very important. According to 2025 public talk by Amy Herzog, there's almost 1.2 billion API call requests per second globally, and API authorization is extremely important. And they were migrating to new middleware or new authorization system. And the core logic was already verified using formal methods. But because formal methods often make assumptions at the, with the verification, at the integration boundaries, we also needed to do property-based testing or end-to-end property-based testing to verify these assumptions at the integration boundaries. So the semantic input generator or well-formed input generator we built achieved what we hoped to achieve. We reduced the test engine development time by 75%, improved coverage by 4%, and detected like 28% more production issues, all compared to hand-code test generator engine built on a framework called the prop test, which is a kind of hypothesis-like library for property-based testing in the Rust language. But I would say what truly changed my heart is not the success of the semantic input generator that I, helped to build. I think what was really changing my heart to me is that what happened after all these bugs are found. All identified issues were remediated prior to production deployment. And in my opinion, this is a stark contrast to how fuzzing research or even academic fuzzing research work. You find a lot of bugs, you curate some, report it, right? Some of them are shallow issues, some may get fixed. And I would say that this success was actually due to strong Oracle, which was like about 80 hand-coded property, I would say Java classes that encodes the semantics of what the system should do. So based on this experience, I'm arguing that specialized fuzzing is actually really useful technology for fast, well-formed input generation, but we must just shift towards property-based testing to really increase actionability. So that means we need to solve a specification problem. Where do these strong oracles come from? How do you know what are the properties that should be validated? And to me, this is a specification problem or intent definition problem. But based on my experience of teaching undergraduate software engineering class, these days, specification is also generated by AI. I find that when I give this task of a requirement specification, I expect the students to think about what the system should do. They create a massive markdown document, very verbose and long, right? To just do the experiment, design the specification. So how do we know these specifications are actually correct? And if correct, how do we know they actually reflect the implementation that's being built? So I envision dual-track validation approach to solve this specification problem. Suppose that you could generate candidate property, such as conjectures or candidate properties. They could be generated by a human being, but also generated using AI agent. It could have a dual track. So one, we could prove whether that is indeed correct property. Then second, we could also do property-based testing to see whether it holds truly on a real system. And there's a really interesting dual symbiotic relationship that you could see. If a PBT succeeds, then it serves as a conjecture that is worth proving. And if proof succeeds, then we must check and see whether it holds on a real system as well as the assumptions used for that verification is actually correct. And I'm not the only one who's recognizing this symbiotic relationship between property-based testing and verification, or verification and testing. There's a lot of people in this room who believe the same idea. Now, the key is, how do we amplify this process of creating lots of properties that is worth validating and also checking? And I read this paper called Patterns in Property Specification and for Finite State Verification when I was a graduate student. This is a paper by Matt Dwyer and his colleague. It won 6 Soft Impact Award a few years ago. And this paper is actually about linear temporal logic patterns and properties that they found that, a lot of people actually use recurring patterns in LTL specification. And, there's in some sense, like a property template for these things. Perhaps this paper resonated with me because of my, bias towards recurring code patterns and code clones. But this, paper really resonated with me. So I wanted to test this hypothesis. If we could harvest and codify recurring property patterns, can we ease proof engineering and check correctness of these conjectures easily? And if we could also codify these recurring validation or property-based testing patterns as a template, can we also amplify generation of a PBT in an effective manner? And as I was coming back from Brazil after attending ICSI in April, this idea got into my brain that I thought maybe I want to try out the agentic proof engineering and property-based testing by leveraging this idea of a property skeleton or a proof skeleton or PBT skeletons. So I reached out to my postdoc, Sungmin, and my PhD student, Theddy, whether we could have a fun experiment. They agreed. And then as a target system, I chose Apache Spark, data-intensive computing framework, which is a really large-scale system, but some system that I've been familiar based on research in the past decade. So let's now talk about what I mean by recurring properties or recurring pattern. So one of the property I would name it is aggregation decomposition in a system like Apache Spark or any other kinds of data-intensive computing framework. Regardless of what schema of data you generate or a data frame that reflects a schema with the different kinds of data payload or what kind of workload query you generate, applying global function on the entire data set has some relation to applying that function on a local partition or subset of a data set and aggregating with a recombiner operation. This is actually one of 8 properties that classes of properties or family of properties that appear in this our recent work. And now let me talk about an example of such instantiation of this recurring pattern. By the way, depending on what you choose as a relation function and recombiner, this property may hold or may not hold. So one example is this a concrete instantiation is a global count is greater than equal to max of a subcount. And another instantiation could be something like unique items are contained in the union or bag of unique items. And basically, if these relations hold, then for aggregation operation, regardless of what data or queries get generated, this relation should hold. And you might be wondering why this is important, because in this data-intensive system, a lot of optimization is built on this idea of predicate push down or aggregation push down, where you move the computation in an earlier stage so that you could actually reduce the cost of materialization and data transfer. And if you think about these recurring patterns, it will be represented as this kind of a like property in first order logic. But what I want you to notice is that there is a relationship that holds between function, recombiner relation. And if that relation holds, then this entire property holds. Okay, let me drink some water. Thank God, I love sparkling water, but this is still water, so. All right. Okay. All right, so now the first question is, can proof of skeletons ease proof engineering? So here, what we actually have done is that we basically wrote the basic data types, functions and relations, and basic theorems in Lean. This is almost like how database or people who are doing data-intensive computing will look at the basic data structures in the computation. And what we're essentially doing is that we create all these basic setups and wrote a proof of skeleton, which I'm going to describe next. And we agentically generate the conjectures and check whether that instantiated property holds by doing like agentic proof engineering. So this slide is a little dense, so please stay with me. So let's go back to that property of aggregation decomposition. Regardless of all kinds of data being generated or workload queries generated, if the relationship holds between recombiner, function, and relation, then this property holds. You could think of this, what's written here is almost abstract theorem. It may hold or may not hold depending on what function recombiner relationship happens. By the way, I'm not expecting you to read this Lean code, but I color-coded so that you could see the pattern. And what it essentially means is that there is a subgoal lemma that actually checks that this relationship between relation, function, and recombiner must hold. So suppose that we give an agent like PySpark API documentation, or it has its own knowledge about what kinds of functions it could be possible in data-intensive system, or what kind of recombiner could be available. Suppose that there is a concrete lemma, such as a global count should be greater than or equal to maximum of a local count. That decomposition lemma, the subgoal lemma, is now instantiated by binding with these concrete functions like count, relations, and max. Then first, we tried to prove this using GPT 5.5 by putting sorry there, so we don't know how to prove it, but ask it agent to prove it. And once the proof is completed, we plug in that lemma to derive that specialized end-to-end property. So what is the benefit of a proof skeleton? So we generated, let's say, 100, property, concrete instantiation of this property, hypothesized by LLM, but also enumerated based on PySpark API. 28 of them are infeasible due to it's not being modeled, or it's actually incorrect property, incorrect conjecture. We find that there are more success in terms of proof with the skeleton than without. The one that could be proved without skeleton is only one. When you think about it, it's actually intuitive. We provide this skeleton or scaffolding structure for proof, which guide which problem to be solved. And also, when proof succeeds in an agentic way, it doesn't mean that proof is correct. There could be hallucination in the proof, such as putting a relation with some true and say a cheat, or recombiner ignores actually input and then compute the result. So we manually investigated this proof of hallucination, and we found that having proof of skeleton reduces the proof of hallucination. All right. Now, let's answer the second part of your question, property-based testing. Does encoding property-based patterns in PBT into a template ease amplification or generation of a property-based test? So in this testing work, we're testing real Apache Spark. And what we did is we created this abstract skeleton. You could think of it as a PBT template, where there are certain methods are like, declared abstract test method that should be filled in. Again, we prepared a well-form input generator, like for schema, data, or like data directed acyclic graph of a computation first, right, as a part of this template. And then what we are doing is we agentically generate like test plan and then generate the generator for test generator so that we could create lots of different kinds of PBT. I'm going to describe this a little bit more in detail in the next 2 slides. So suppose that there is a properties that you know as a correct or hypothesized by AI, such as like for all data and compute workload, global count is the sum of the local count. We use agent to actually select the relevant APIs in a PySpark. So for example, for function and recombine and a relation, we could find that these count sum equal. I wrote it like very, briefly here, but like it's a fully qualified type name based on the documentation. Then what is this skeleton? This skeleton you could think of as an abstract class with the holes. By the way, you don't try to read this. I purposely made it this way. What this abstract superclass means is that if you are familiar with the idea of, let's say, like program sketching or synthesis with a hole, there are certain holes to be filled in. And so for example, you could change the global like computation or local computation with the recombine operation and also the check that's required for Oracle. Again, we use agent, given the test plan that's generated, to override these abstract methods and fill in this slot. Then you generate the test generator, which now generates lots of property-based tests. And here's our result. PBT skeletons increase the test diversity in terms of operator being exercised, because there are many data frame operators out there, as well as there's a lot of functions that are available in Apache Spark. These functions are all designed because when people use the existing API, that actually makes optimization easier. And we compare against like generating PBT, just asking LLM to generate PBT, like in hypothesis like test. Library test. There are actually the product by out there, which is called like PBT Kiro, which is like asking LLM to generate property-based tests. And some of you know that there are like some existing way of generating these PBT by looking at the round trip properties or idempotent property pattern. So we find that this approach could increase the diversity of a test. And when we compare against like fuzzing, we actually found that this PBT skeletons match the fuzzing's coverage. So both are actually really benefiting from this power of a random generation. This coverage is also, in this case, more effective than generating PBT using AI with the 0-shot learning or 3-shot learning. But what I'm really excited about is the kind of errors that's being detected. So many of you who have experience of fuzzing, if you run the fuzzer, like you get a lot of input invalidation errors. Some of them are a type mismatch, like all because you're generating, like in some sense, an invalid input. But when you are using these PBT skeleton now, like category of error is shifting into a little bit more actionable category, which shows a deviation from intent, such as the discrepancy between like math and actually how implementation worked, or like a numerical instability, or discovering issues with the API naming that makes these like PBT generation or client usage kind of confusing, or true like implementation bug. Now, I wanted to kind of share another result on this PBT skeleton. And this is a collaboration work with Yuxin Chu, who's a Professor Qian Zhang's student at UC Riverside. I talked a little bit about like part of my work was recently looking at hardware heterogeneity or hardware compilation. So we wanted to test the same idea in deep learning compiler called the TVM. Again, TVM has a very large of operators. And using the same idea of a property skeleton, we wrote 20 property skeleton, applied to 212 operators, and generating almost 5,000 PBT tests to test this system. And all these skeletons are actually encoding tensor algebraic knowledge about what the computation should do. And again, we're finding that PBT skeletons match fuzzing's discovery power. We compared against PBT LLM, again, asking AI to generate property-based tests. We find that coverage is actually lower, but when you look at PBT LLM's coverage, they're actually coming from all error handling logic, right? Which is not actually, interesting, or it's kind of misleading because these coverage are not really actionable. Then again, we are finding the shift in the error that a lot of errors actually found using fuzzers, and then a lot of them are input invalidation errors where generate tensors do not match the expected shape or type, or some of them are model compilation error, which means that the computation graph itself or model itself is ill-formed. But now the found errors are shifted to math and implementation inconsistency, numerical instability, API misuses, or mismatch from a reference oracle. All right, we're at the 38-minute mark. Great. So what next? I think coding models or AI will probably get better and better every day. As they generate new models, there's a clear that, that acceleration speed will get better and better. So in my opinion, we not only need to catch up, the innovation speed of validation not only need to catch up this speed of AI-enabled generation and creation, but must outpace the innovation speed of these coding and generation. Why? Because code is increasing surfaces, there will be still bug remaining or security vulnerability that's propagated by AI models. So before we look towards the future, it's worth taking a step back and appreciate what the programming language and software engineering community have done on the space of research problems that I talked about today. We came a long way. Starting from the seminal paper on quick check, there has been libraries like Hypothesis being built. There has been, these PBT input generator based on inductive relations, working with ROC or Lean. And then some of these work have moved on and making impact in practice, like a Jane Street with the financial software. And some of the work was also inspired or influenced by these advances in coverage-guided or search-based testing. In the fuzzing, it kind of moved on from fuzzing to generation fuzzing by adding more constraints on the input space. Ability to search and navigate space better with the coverage guidance. There's an explosion of work happening after AFL or American Fuzzy Law. Moved on to a little bit more space of a stateful fuzzing, semantic fuzzing, and also quantification using statistical analysis to quantify this residual risk or absence of errors. And also this specification problem that I talk about also has a long history, starting from some of the well-known work like a DICON or a Deduce that try to understand specs from executions. I think this community has done fantastic foundational work, reasoning about program specification or generating programs with the specification in the context of incomplete or ambiguous intent using data, tests, and examples. And these work shifted towards neurosymbolic synthesis. So this is fantastic, a lot of foundational work. And I have a question for us. We are getting a check-in that is at the speed of 10,000, 100,000 lines per commit, right? How are we going to scale this technology to work at this speed? And I'm not just talking about computational scaling of underlying like SMT solvers or verifiers. I'm talking about cognitive scaling required for inspecting the specification or the results that are generated by these techniques. As one such idea I have is this Socratic end-to-end validation. As a professor, we don't read every single line of code that our students write. We ask questions, right? And these questions are very insightful and informative, and often comes with an experiences. So why review 10,000 lines of a generic unit test where you don't have a time to read individual test oracles one by one? What if we could ask questions in natural languages and a concise summary of a property-based test with the statistical confidence or very few counterexamples? And I could imagine that this could be done if we could identify these recurring patterns and then also have a technique that could boost and bootstrap well-formed input generator, as well as plug in these skeleton oracles with the strong oracles. And I think the homework for this community or verification is how do we do this also for the verification side as well? I have that question for us. I think right now is a really exciting time for the field of auto formalization and verification. My colleagues in the math and physics, quantum information science, computer science theory, are getting really excited about moving towards mechanicalized proof. There are also tools and services such as automating reasoning check that support this auto formalization. And I think that this is a really exciting opportunity to mine recurring patterns or proof. And I could imagine that this could actually accelerate existing work on proof engineering in terms of theorem discovery, lemma synthesis, as well as a neural theorem proving using AI. There's a lot of work that can be done. But I'm also really excited about the potential that in individual domain, we could now codify what are the recurring properties or invariant and the correctness structure that could guide the PBT or test generation that could really accelerate this process in a symbiotic way. So, I think going beyond the round trip properties or these idempotent properties, we could probably understand what are these domain specific invariants or properties that could bootstrap the testing engines. And then last, I imagine that there will be more and more migration, rewriting, and innovation to new languages, new platforms, and rewriting all legacy code powered by this AI. It's not going to be just a temptation. It's going to be competing with your competitors for innovation speed. And there will be a lot of work that will be happening in terms of rewriting. And to me, this is not an only issue of correctness, but it's also performance as well. People are not going to migrate to new thing if it is completely correct, but it also has to be fast and high performing. And I believe that this could be also enabled together with this control property-based testing, because when I think about this well-formed input generator, if you put a control on data distribution size or complexity on computation, that itself is actually almost a performance workload generator. And if you combine that with the latency and throughput measurement, it could really drive the innovation by both ensuring correctness and performance. All right, so this is my last slide. I think one of my PhD students asked me, why is your keynote titled The Happiness U-Curve? Is it because you are age 47 and the rock bottom of a midlife sub? Partially true. I got so excited about this book, and I find it eye-opening. Oh my God, I understand why. But I also think this is a happiness U-curve for our community, because this is a transition point of optimism, new problems, and new challenges that we must solve together. we worked a lot on like creation by leveraging recurring patterns in code. And this might be a time that we should move towards validation by identifying and leveraging recurring pattern in validation, and then by enabling also like other kinds of science who wants to move to these kinds of verification and validation powered by AI. All right, so I want to thank my postdoc Sangmin and my PhD student Seti and Professor Chan Jiang's student Yushin. They have done incredible work that I am grateful for, and I also want to thank them for tolerating my enthusiasm as a middle-aged Korean lady professor who suggested that we should meet every day to get this result going. So I'm super thankful to them. And I also want to thank my friends and colleagues who reviewed these slides with me and then, gave me comments. I'm not going to name name all of you, but I want to share my gratitude. And I thank you for friendship and support. And I also want to thank funding agencies that supported this research, National Foundation, AWS, and Samsung. And I am very grateful for the work that's happening within my team, Amazon Science of Security, that really inspired this line of work, and also broader like automated reasoning community. In fact, like automated reasoning at AWS is hiring. All right. So with that, thank you.
Okay, thanks for the great talk. We have a good amount of time for questions, so please come up to the mics. And yeah, Danny.
All right. Is this on?
I think so.
It should be on, yes. Good. Happy Thursday, everyone. I'm Danny Dick, one of your friendly professors from CU Boulder, so we are glad you are here. Mir-Young, thank you so much. You inspired us on the research side, but I know you are a leader in software engineering research, also in education, and I'm looking forward to you inspire us on the education side as well. Just a small anecdote. Last summer, I was invited to speak about generative AI-powered software engineering at universities on 4 continents. Every professor who is teaching PL or software engineering classes tells me the same story. Yeah. Students turning perfect homeworks, yet at the final exam, when they don't have access to Gen AI, they fail. So somehow we are failing to teach students to use generative AI to make themselves smarter, not lazier. How can we turn this U-shape, this curve, I loved your U-shaped curve. I think we are at the bottom right now in education as well. Yeah. How do we turn this curve so that we inspire students so they can learn more, not less with AI?
Okay, that's a great question. I think many of academics actually share the same concerns and questions too. So I could just share my own personal view. I think some of my colleagues believe like how we should teach vibe coding skills, right? Or how to organize it so the agent understands better. I might be a little bit old school, but I am actually thinking that fundamental reasoning skills might be more important. Like, for example, like, proof or like, inductive reasoning or like, so if you are asking like, I'm trying to teach my daughter like, what is a proof? Because I think to me, these foundation skills might be more important than some of these transient skills that may be required, because also agents or interactions are evolving very fast too. But anyway, that's my personal opinion. Yeah,
I agree. Thank you.
Hi, Harry Goldstein, University at Buffalo. Yeah. Great talk. Thank you so much. I'm very excited to see property-based testing talked about so much here. In your property-based testing skeletons work, how much of those skeletons were domain-specific versus how many could kind of translate out? Because in my work, I've found that like sometimes these skeletons end up being kind of specific, and it could just sort of push the problem up one level, and now developers have to come up with a skeleton, which is also hard.
Yes. Great question. So I think this property-based testing, I use loose, but I also want to contrast from how property-based testing, for example, in your study at Jane Street is talking about. So in your study or in the study done by Harry and other people, the the property-based test is actually usually done at the granularity of functions in OCaml languages, and it's almost a generalization of a unit test. The way that I described is actually more end-to-end property-based testing, where there is a lot of groundwork done in terms of well-formed input generation. So for example, we have ability to generate the schema, we have the ability to generate the data frame, and that data frame must match the computation shape that's also generated to match. So it's very domain specialized. I'm not saying that that is a way that we should do or we should start making one at a time. I wanted to check the potential that if we have something like this, how much we could get out of it. I could totally imagine that we have to move towards a space of being able to synthesize these things, right? I think some of the work done in this well-formed input generation shows the potential, but I do think there's a lot of research to be done in terms of that automation, right?
Great, thank you.
Hi, James Lee Jones from Imperial College London, and very interesting talk, thank you. And so I have a couple questions, I guess.
Yeah.
The first one is somewhat similar, which is that in your Apache Spark work, did you write these skeletons yourself? Because I can imagine that coming up with some skeletons may be just as hard as coming up with oracles in the first place. And I suppose the second question is that in a lot of your slides, you compared against fuzzing generally. And I would kind of argue that fuzzing and property-based testing are the same thing, just looked at slightly differently. And it's entirely possible to come up with fuzzers that generate well-formed input. So as an example, CSmith by John Regeer's group. And in that case, you wouldn't have the problem of generating so many ill-formed inputs. And so I was curious what fuzzers you were comparing against here.
I see. So in that case, so let me first clarify. So in the case of actually the PBT skeleton versus fuzzing comparison for Apache Spark, we use a fuzzer called the Comet fuzz. It's like one form of a specialized fuzzer for that domain, but it's also still generating some invalid input. I also want to mention that the category of this XSmith, whether it's a type fuzz or CSmith or like for type fuzz for SMT or CSmith or SQL Smith for SQL, it has a higher chance of generating well-formed input, but also it could generate input that's like considered invalid as well. So in the TVM comparison, we use one of those like kind of specialized fuzzer, right? But still generates like, in some sense, some of these ill-formed input, right? What was your first question?
I can imagine that it's just as hard to write these skeletons as it is to come up with oracles.
Yes. So I think this writing the skeletons are actually very hard. And then I think this is a kind of recurring problem. Even if we lift to the abstraction level of, let's say, property family or, skeleton family, I think there is some domain knowledge that has to go in. As I said, I fully acknowledge that it would have not been possible unless I've been kind of circling around this domain, like for the past 10 years. And also thanks to my student who also review some of the related literatures in this space to come up with this relationship, right? How do we really bootstrap this fully automatically? I don't know. But I'm actually hopeful because I think there is more work going into this auto-formalization, and I think this may unlock some potential in terms of recognizing what are the correctness structure in a given domain. Yeah.
Thank you.
Hi, Sriram from Brown University. Hey, Mariang. So I really enjoyed the technical aspect of the work. I still feel like this epistemological frustration, which I've always felt with property mining as well, which I think your PBT stuff is a kind of property mining, where the idea of verification was supposed to be we have a redundant, hopefully redundant statement about what's happening, and therefore we're going to be able to tell whether that is in fact what's happening or not. And if we vibe code the property and that's going to be having the same correlated failures, we haven't learned something new. It's useful, of course, if I want to do maintenance, like you said, the code might have changed and I can use those old properties. But I feel like, especially in the PL community, we should be thinking more about how to help the slightly more responsible programmer who wants to write a property but isn't willing to do a lot of work for it than the one who wants to just vibe code the property entirely. So I see your Socratic proposal. I don't quite buy that because I think the problem is we have a lot of knowledge now about misconceptions that people have, and misconceptions tend to be in the mismatch between the formal and the informal. And so they're just going to end up like circulating back, and people will be like, yes, I have Socratically approved of this thing, and we're actually worse off because we've just encoded the thing that they misunderstood.
Yeah. Shuriel, I absolutely agree with you. So I'm going to acknowledge the part that, in some sense, the property skeleton we have seen, some of you who are familiar with the DICOM may find relation that there's a template, there's instantiation, we're checking what holds, right? And I think for those of us who use like DICOM as an invariant mining, we all know how many false positives it creates. So I think this encoding of the right structure is really important. I also do not think it actually obviates the whole process of actually thinking harder about verification and validation and specification. So I know like there is a proponent of this slow pace coding in the era of AI, which I think there's a really valid point there.
There are more interesting midpoints between
Yeah, midpoint, right? So I don't know all the answers to this question, but I do think we are at a very interesting transition point where these are like thinking harder about specifications and what the intent is. We need to scale up very fast, right? And I think that's a challenge. So sorry for not providing answer, but I think it's an exciting problem we could solve.
Hi, thank you for the intriguing talk. When I was thinking, Brendan Constein from Bethlehem, New Hampshire, I'm curious about the validation and bottleneck. You're talking a little bit about scaling up the cognitive tools to handle these complex validation verification tasks. And you talked a little bit about the skeleton, where you're mixing these references in and out of scope, and you have a lot of generating the generator for to test the property that you care about. And one thing the PL community has thought very carefully about is type-safe metaprogramming. I was talking to someone about hallucination over these metaprogramming tasks. And it seems like if you're generating the low-level code directly, models tend to hallucinate quite a bit. But there are frameworks for stage metaprogramming and type theories for doing this kind of hole filling in a safe way. I was wondering if your thoughts about that, if it's time to scale those techniques or put them into production, and how you feel about the PL approach to that. Thank you.
Thank you. So I am not a programming language person, but I am like aware of exciting work that's going on in type system at a kind of the outsider view. And I think all these, wonderful work done on the type system or meta theory is actually really important, because what I talked about is a little bit more of a like higher order pattern that you see. And I think if we could be checked using like type theory, I think that is a wonderful thing, because maybe one thing that we could do is also codifying this, right, with the maybe help of a type system, right, that could be verified before you try to bootstrap these like property generation or concretization as a test, right? So yeah.
Thank you.
Nick Swami, Microsoft Research. Great talk, really enjoyed it. I have one remark and one question. The remark is, there was a part of your presentation about proof hallucination, and actually I think I understood it not as proof hallucination, but as specification hallucination, where the agent has inferred a bogus definition of the property that is to be proven, and the proof is still correct, but what has been proven is meaningless.
That's right. Absolutely.
So I think this kind of reinforces your message really about it's about getting the specs right. The proofs are symbolically checked. So that was my first.
That's right. The proof succeeded from the lean compiler perspective.
Indeed, yeah.
But then the definitions that are used for making proof succeed is like incorrect.
Right. And so auditing specs, making sure that intent is precise. I think that's really where our attention should be. So that was my remark. My question was, you spoke a lot about generating well-formed input, and another question there was about illegal inputs. I wonder what you think about adversarial inputs and how to generate that, because a lot of the security bugs lie at the boundary where inputs are misinterpreted and well-chosen adversarial inputs, I think, are also an important part of this testing story. And AI seems to also help here with, as we know about from recent news around the Mythos-style models and related things. I wonder what your perspective is on that.
Absolutely. So the Wolfram, there is actually a paper called Inputs by Hell, by Andrew Izello's group, which is actually inverting this problem of a Wolfram input generation as a probabilistic generator, but inverting it so that you increase the likelihood of seeing unseen or unexpected input. I think there is a new line of work coming from both the communities, and some papers are coming here, which is actually systematically controlling that generation probabilities to skew the distribution so that it's more likely to be correct or similar to what you have seen. But then you could also use the same idea by inverting it and generate this potentially adversarial or unexpected input, right? And I think that goes with the kind of my last slides a little bit. I think we should think about this Wolfram input generator almost like a synthetic workload or a synthetic input generator with the control, so that you could change the distribution. And if you want to do adversarial testing, it goes to that direction. If we try to emulate more seen input, I think it goes to that direction. Yeah.
Hi, Miriam. This is Shubhendu Lahiri from Microsoft Research. And thanks for the talk, wonderful talk. And thanks for the nod to the intent formalization work that many of us at MSR has been doing last few years. Yeah. My comment was this. We've thought about property-based testing, but it requires an implementation, right? Yeah. That's my understanding. So we have been thinking a lot about testing specs without an implementation. And because my feeling is that once the code is there, the users lose the reason to look at a spec, right? So I think property-based testing is great, but I think we could aspire for more.
Yes, absolutely. So Shubhendu mentioned his recent paper I actually cited called the intent formalization, and then there is this idea of a small proof-oriented test. So these are not executable tests, but this is almost in a form that defines the input-output relations, which could be used together with the auto verifier. I think there is definitely that space of specifying this intent in terms of not executable tests, but relational tests that relates input and output, right? So I think we are all talking the same kind of, seeing the potential where testing and verification could help. I think we should really think about together how to amplify this, right? So.
So Nengkun Yu from, Nengkun Yu from Stony Brook. So I'm wondering about the property-based testing. So I think there will be, so you generate lots of properties, let's say, and different properties would verify different properties, or testing different properties would correspond to different resource of costs, like implementation time, and you need many samples. And do you have a systematic method of manipulating what order of the property to be tested?
Order of a property to be tested.
Or what properties do you want to test?
Okay, so I want to tease apart two parts of the question. So the question is what property to test or how to do this generation.
Because they have different resources.
Right. So I think actually I talked about today end-to-end property testing, almost like a functional view or end-to-end where you could actually do invocation and then you could check the output. But one problem that I actually gloss over is property testing in the context of a stateful system where state must be constructed and there might be ordering or side effect that's coming from execution. And I think there is something that we actually have to figure out. And there's also not clear mapping between how theorems translate to property-based tests, because the theorems or verifications you use these ghost variable or state that doesn't actually really easily map to this input generation with a for all quantifier, or you need a clever way of filtering this. So that's one question. The second part question was, what was it?
Different properties would use different resources, many samples. Some would cost more samples, and some the algorithm implementation would cost
I see.
longer time
So
and
I think
things.
the second question is actually distribution of input or thinking about search space.
Yeah.
I think there is a really exciting work coming from this community as well as a community in software engineering. I think this input space exploration and understanding the confidence associated with the input space is a really important question. I'm looking forward to attending some of the actual papers on that topic today. There's also work on quantifying confidence associated with the fuzzing campaign or state search space using statistical analysis. Like, you know, that's a kind of new line of work that's popular in software engineering. So I think we could consider the kind of two together, right? One is measuring, and the other one is also like how to control it with this like systematic control. Yeah.
Thank you.
Okay, let's thank the speaker again. Wonderful. Thanks so much, Marianne.
Thank you.
Okay, and now it's break time.
Thank you.